And it is my pleasure to introduce our first speaker this morning, Lukasz Grabowski from the University of Leipzig, who will be speaking about Connes-Weiss and Glasner-Weiss theorem for carbon equivalence relations and application to cost.
Thank you very much. It's a great pleasure to be here. Thanks for having me. I'm going to be talking about joint work with my PhD student, Hector, Jardon, Sanchez, and Sam Mellick. I want to start with, so this is a talk about essentially about property T. However, I would like to start with something which is only loosely related, because I know that there are people who know three manifolds in the audience, and I want to use it to my advantage because I have some questions about them. So this is only loosely related. However, this was my motivation, or one of my motivations for this project about property T. So let me start with this loosely related part and move quickly to property T. So I want to remind you about homology gradients, just as a way of motivation. So we have the following situation. Let's suppose that M is let M be a triangulated, aspherical, closed three manifold, and suppose that we have a sequence of covers. So let's call M M0, and suppose that we have a sequence of covers of this manifold, which converges to the universal cover in the obvious sense. So such that, so converging the universal cover and twiddle. And then we have the following theorem due to, I will say, Lot and Luke here, that the homology gradient of the sequence vanishes. So what I mean by this is that if we look at the dimensions of at the Betti numbers, so dimension of homology of this manifold, and we divide here, I took them triangulated, so I'm going to just take the number of vertices in the triangulation, number of vertices of Mi. This converges to 0. And let me give you not so much a sketch of the proof, but let's say overview of this proof, how it proceeds. Sketch of proof. So first is so-called Luke approximation, which is a statement that so this dimension is the Betti number. So I just am going to use the B1 Mi for this. The Betti number divided by this, so normalized by the number of vertices. This always converges to 1 divided by, we have this normalizing factor which doesn't matter here, and this converges to the L2 Betti number, so the dimension of the L2 cohomology of the universal cover. So this is Luke approximation, and then so this is sort of the first step, and the second step is we just compute the L2 cohomology of this universal cover. So we show this is 0, and this I will say, of course, this is a very long paper which has this result, but this can be checked using using classification of three manifolds. So using classification of three manifolds. Okay, so that's a very nice statement. I don't know any other essentially different proof of the fact that those homology gradients converge to 0. If you do know something which in particular does not use classification, I would really be keen to hear about this. Now, how is this related to anything measurable? Okay, we have L2 Betti numbers, but maybe maybe some more tangible relation. So let me now ask a question. So now suppose, and this is really the reason why I want to do this introduction. So let's now suppose that we have a sequence of triangulated manifolds. They don't come from covers of a particular manifold. At least we don't assume this. So let this be. So this is a sequence of triangulated three manifolds. And here I will just assume that injectivity radius of those manifolds goes to infinity. So what would be the injectivity radius? So I just look at a ball, and these are triangulated. So I can look at the radius r ball in the graph distance, and I can check if there is any non-trivial topology there, and there shouldn't be any. So injectivity radius, this would be the maximal number r, such that for every, let's say for every x in the manifold, this ball bxr, this is the graph distance really. So I'm looking at all the vertices which are at distance r, and all the cells which I can take here. So assume this is contractible. And then the question is, can we deduce the same result? So this is now really the assumptions for the questions, and the actual question is it true that the dimension of this first homology divided by the number of vertices goes to 0? So the question is, if you know three manifolds, maybe you can just tell me, and we don't need any measurable stuff, because let's try to imitate this log proof and see what goes. So what would be the strategy without log of generality? Assume those mi converge in the Benjamini-Schramm sense now, in the Benjamini-Schramm sense to a measured triangulation of R3. So here, what I mean is we have a graphing, we add 2 cells to this graphing, we add 3 cells to this graphing, and we just want every component to be homeomorphic to R3. So that's what measured triangulation of R3 is. Okay, but so let's call this measured triangulation of R3. Let's call this M. And now the question is, so that part is fine. We still have that this homology gradient is equal to the first L2 Betty number of this measured object. But it is interesting to ask whether indeed the first L2 Betty number of this is equal to 0. Okay, so this is now the question. And if there is somebody really brave and young and knows PDEs, then they could just maybe take what Perelman did and do it measurably. And this would be a fantastic work. Classify the measured geometries of R3. I think this is a very nice project, but I'm really asking this because maybe if you know enough about three manifolds, then maybe you don't need to do measured geometrization program, and maybe you can deduce things like this more directly. So if you have any thoughts about this, I would be very keen to hear. Since we are already here, let me ask this. Like an interesting question is whether do we actually get, when we look at those measured geometries, do we get anything more than just by looking at groups and covers of manifolds? So for example, Okay, we can ask this kind of question. Assume M is ergodic. Is M orbit equivalent to pi1 of M, where M is closed aspherical three-manifold? And now we finally see why maybe this has anything to do with property T, because if you wanted to answer this question, then maybe you can first ask the following question. So can this relation, and I will say what it means more, can this relation, equivalence relation, be Kazhdan? This is question which is related to this one, because we know again from classification that those groups never have property T. So if you somehow found a measured triangulation of R3 which had property T, then you would answer this this question. Okay. Right. So now we're gonna just move to studying property T. Okay. So now is really the main part of the talk. I normally do not include this part. I decided to do it because this is a geometric group theory program, and I thought that maybe, you know, there is somebody in the audience which could help with those questions. So now is really the part one. So I want to remind you about some general properties of property T, in particular in the case of groups, and how we can generalize them to equivalence relations. So general. Was there a question? No. General.
So can you say anything about the triangle? Do you know anything, any properties of it about this M?
I mean, if I don't know if you get substantially more than when you just look at groups. So it would be interesting to find, you know, answer to this one. Like, can you get something actually new?
But okay, but this thing doesn't come. It's just it doesn't come with a group action or anything. It's just this. It's the unimodular equivalence relation.
It's a measured triangulation of R3. In particular, there's an equivalence relation, which.
Yeah, but I mean, it's. I mean. It's not the same measure, it's still like it's measured to different respects.
Yes, you start with a graphing. You start with a one skeleton of R3, which is just a graphing. And then you measurably add 2 cells and 3 cells to the graphing.
I guess it's Sophie?
No, I don't know that. No, I mean this would. So this is another thing, but this is not related to this one. But yeah, I mean, no, we don't even know for planar graphings whether they are Sophic or not. So even less here, but no, I don't know that. No, okay, so
sorry, guys, it's just naive question. When you say triangulation, so you mean like, you know, the equivalence classes are the triangles, right? Or what do you mean?
The triangle. So I mean, start with the graphing, and
graphing of what? Any graphing.
I will just start with the graphing first.
Okay.
And then add 2 cells measurably. That makes sense, and 3 cells measurably. And now I just assume abstractly that every connected component of this complex is homeomorphic to R3. Okay. And I call this kind of object measured R3.
But so your graphing is like countable connected components, right?
Yeah.
Okay.
Are the MRs compact?
Yeah.
So then isn't it Sophie just because it's a limit of it's a intermediate strong limit of the.
I mean, no, yeah, in this sense, yes. That's why, yes, of course. If you just take it for the purpose of proving this theorem, then but if you just take measured triangulation. Oh yes, of course, yes. Yeah, sorry, I misunderstood you.
I just thought maybe there was more information, and there is some more information.
Yeah.
In this, so, okay.
And so this question means like you want this equivalence relation to be orbit equivalent to a group, this group.
To this group, because I mean the question.
What does that mean? That means that.
So how you can construct this kind of measured triangulation of R3? Well, you can just take a group which acts compactly on R3 on some geometry. Let's say you take, I don't know, Z3. And Z3 gives you this kind of measured triangulation because you can take any free action of Z3 and you add the obvious 2 cells, obvious 3 cells. Well, you got yourself a Euclidean space.
So this question is does this come from what such a natural action or PMP action?
Yeah, like is it or is it not true that by using out those measured geometries we get some new wild world, or is it just, you know, yeah?
I don't understand the question there. You have triangulated many points, but you have no normalization. I mean, V is the number of vertices.
That's right, yeah.
You can subdivide and add
Yeah.
a lot of.
Yeah, but then the gradient is 0, and that's then true because so no counterexample here. But
they always make it
I'm
going to 0.
Yeah, but I start with a sequence. So now suppose, you know, I'm just given a sequence of manifolds and I don't know anything about them. I just know that they look more and more like R3. And is this enough to say that the homology gradient goes to 0? Okay, so that's I think it's, you know, these are really interesting questions. If you have some ideas about them, please do let me know. So let's now move to the main part. So generalizations of theorems about T from groups to graphings and to PNP equivalence relations. So let me just state 3 or so theorems about groups. Okay, so let G. We will assume for simplicity that G is a finitely generated group, so that the statements are slightly easier. We have a symmetric generating set. The key definitions about actions of such a group are when the action is expanding and when it's strongly ergodic. I believe that Damian introduced those notions last week, but let me remind you about them. So an ergodic PMP action G on X mu is expanding if for every delta there exists an epsilon such that for every u such that the measure of u is at most 1 minus delta, we have an expansion. So if we look at u together with where u is sent by S, then this expanded in measure multiplicatively. And a related notion is, so let's say this is A is expanding, and the related notion is strongly ergodic. This is not useful for this talk, but traditionally one of the theorems is stated with strong ergodicity, so I will use this as well. So if for every delta, so the same thing, but now we assume that U also cannot be too small of a set. So for every delta, there exists an epsilon such that for every U, if the measure of U is between delta and 1 minus delta, then we have an expansion. So mu U S U 1 plus epsilon times mu U. And then, of course, the way it's written here makes it clear that expanding implies strongly ergodic. And in general, there is no implication in the other direction. And now we have the following. Yes?
So probably in the first one, you could use the less quantifiers and go with the standard final, but with this work methodology.
Yeah, yes. Here we can just remove delta and assume that we have expansion up to 3/4, let's say. So I thought I will avoid one question if I state it this way, namely, how can you see that expanding implies strongly ergodic? And I did. However, the number of total questions has been preserved. Okay, so we have the following characterization of groups with property T. This is Connes-Weiss. The following are equivalent. G has T. For every ergodic PMP action is strongly ergodic, and every such action is expanding. And another key property of actions is the Glasner-Weiss theorem. So again, so now we assume that G has T. Suppose G has T, and let G xi mu I be a sequence of ergodic actions which weakly converge to another action, and then this action is also ergodic. Then this final action is ergodic. And essentially what this says is that so a useful way to think about it is that all those actions which we have here are actually uniformly expanding. So there is an epsilon which works for all actions. Okay, and the final theorem about groups is Kazhdan's theorem about lattices. So here we let G be a locally compact group, and we take a lattice. Then G has T if and only if gamma has T. Also, I haven't said this explicitly, but I think that even if you, I mean, if you don't know how T is usually defined, then Connes-Weiss allows you to just take this as a definition, and it's a very nice, very useful definition that all actions are expanding. Okay.
When you're saying that the actions don't mean like the spaces on which we act, like in
so do you know local global convergence, maybe, of graphings?
We can take the spaces the same.
You can take spaces the same. It's just not usually useful for me. But it means Benjamin-Schramm convergence also when you add colors, basically.
The G action is the same. So the G action is the same all the time, and what converges just the sequence of measures. Yeah.
Yeah, I suppose. Yeah. Yeah, adding xi here does not increase generality because it's a measurable statement, but okay. I mean, in examples, it's usually
the way Glasner-Weiss stated it. They did it for like shift and invariant measures. So they did it just like you said. They took the shift action of the group and just looked at all invariant measures. And said it's close, and the ergodic ones are close.
To make sense of reconvergence, like you need a topology, so it should be like shift space. Reconvergence is about convergence of methods.
You're right. Yes. So yes. Okay. Thank you. Now I got your question. Sorry. Okay. So indeed, this is better, and we fix topology on X to make sure that weakly makes sense. Okay. So. Okay, so I would like to talk about generalizations of those theorems to the context of equivalence relations and graphings. So first of all, also to simplify a discussion, when I say a graphing, I will always mean that these are uniformly locally finite. And I should say that a lot of so property T for equivalence relation has been studied by many people. In particular, a lot of foundational results have been figured out in so some reference is Michael Pichot PhD thesis. It does not contain, you know, analogs of those theorems, but it has a lot of foundational material. It's extremely well presented and nice to read. Okay, so to explain the statements of those theorems in the context of graphings and equivalence relations, we need to define what is an extension of graphings. So here is our setup. Suppose H and G are graphings with vertex sets X and Y respectively. And now let's have the measure here, X mu and Y nu. And then pi, a map from X to Y, is an extension. Normally, I would write here class bijective extension, but in this talk, this is the all extension. So if you are confused why I'm not using class bijective extension, it's because I don't need it. So I will just write extension. So pi X to Y is an extension. If pi is a Borel map of graphs, and on each connected component of G, it should be an isomorphism. So isomorphic when restricted to connected components of G, and such that push forward of the measure here, nu is equal to nu.
But I think you wrote H as the one on X, so you understood that you wanted to be restricted to components of H.
Yeah, thank you. And a typical example, so extension just means that you add a little bit of extra structure so that we can talk about more Borel sets. Talking about extension is the same as talking about probabilists say this in terms of Borel sigma algebra, but I don't remember the expression that you have Borel sigma algebra and you have what, quotient sigma algebra, or okay, I don't remember. Sorry, I shouldn't have made this comment, but I know that probabilists use slightly different language here. Invariant Borel sigma algebra, I think, maybe. I don't know. Sorry, I will not. No, let's not talk about that.
I'm sure I'm not a probabilist, but I think what you need to say that this is adding randomness and
No. There is an expression which involves sigma algebras.
That the one downstairs is an invariant sub-sigma algebra.
Yeah, something like that. I know there is a right way to say this, but okay, I don't have to use that language. Okay, but examples, just to have something in mind is for example the Bernoulli extension. So if G is a graphing, then we can construct a Bernoulli extension by adding IID 0, 1 value to each vertex. And this is precise. This is a precise definition, but you can also define it using cocycles, which I'm not going to do. It's as precise. And it's important that we understand that this definition is as precise as the one with cocycles. But if you haven't yet wrapped your head around how this can be precisely made using cocycles, then ask me afterwards and I can elaborate. But with this notion of extension, we can now state our theorems, which we manage to generalize. So theorem, this is now our joint work. So first, Connes-Weiss. The following are equivalent. The relation of this graphing has T, which I haven't defined, and as with Connes-Weiss, I think that the other 2 points can be used for definitions if you haven't seen this definition. So for any extension H G and okay, if H is ergodic, then it's strongly ergodic. And for any extension, if H is ergodic, then it's expanding. Okay, so that's what property T is. We look at all the possibilities of adding Borel sets, and there is no way to get invariant sets.
So you're assuming G is ergodic?
I'm just thinking about whether I have to.
Otherwise, I'll just say if H is relatively ergodic.
Yes, let's say G is ergodic. Let G be ergodic. Okay. It's also convenient to talk about property T not just for a graphing, but for the actual measure which the graphing gives. So the unimodular random graph which is given by G. So remark, this will be useful when we state the Glasner-Weiss theorem. If G is a graphing, then we can consider lambda to be the unimodular random graph of G. So what I mean by this is the actual measure on rooted graphs. And then because of this characterization, it actually makes sense to state the following definition. So we say lambda has T if there exists, or equivalently for every, so let's say exists ergodic G such that lambda is the measure, is the graph given by this graphing, and such that relation of G has T. Okay, and actually there are even examples which are not groups but which are deterministic and which have T. That's just an aside remark. But with this definition, it's now easy to state what Glasner-Weiss is. So this is a continuation of our theorem, Glasner-Weiss. So suppose lambda is URG with T. Suppose GI is a sequence of graphings, of ergodic graphings, such that all of those URGs are the same. So URG of GI is this graph lambda. And now suppose this is what I should have said so that we avoid this problem with weekly, but now I will. Suppose GI locally, globally converge to G infinity, some other graphing, then okay, then something which is completely obvious is that the URG of this G infinity is also lambda, just to get it out of the way. But the point is really that G infinity is ergodic, and G infinity is ergodic. Okay, and the final theorem which we can generalize is this Kazhdan's theorem. So let me maybe write it below here. The point is that sometimes a group does not have any lattices and it has T. Locally compact group can have lattices, can have no lattice and it still has T. Can we still extract something countable which has T out of it? And the answer is that yes. finally Poisson point processes are useful for something. So this is our generalization of Kazhdan's theorem. Let G be a locally compact unimodular group, and let M mu be a point process, be an essentially free point process. So M is the space of configuration. So M consists of countable subsets of the group, and we have and we have this kind of invariant measure which some talked about in his talk, and then the statement is that I will state it like this: if G has T, then this equivalence relation of this has T. So then the relation of this process has T. And the remark which I asked Emmanuel Capras if he knows examples which I just said. So this is a remark due to him. I think people who know more about representation theory so on can figure out this example, but I will just state it like this: that there exists a G locally compact unimodular with T.
T already implies unimodular, right? Because it's the image under the modular homomorphism has to be a property T subgroup of R.
You're right, yes. Locally compact with T without lattices. And then one could say that this theorem gives us really new interesting examples of graphings with property T, which do not come in any obvious way from a group action. How much time do I have? 10 minutes, okay. So finally, I want to talk about cost and the theorem of Hutchcroft-Pete about cost of groups. So this is sort of the end of this part where we talk about general properties of property T, or let's say classical properties. And here, let me tell you the theorem of Hutchcroft and Pete, which in particular uses some of those general theorems, in particular Glasner-Weiss. So Hutchcroft-Pete, suppose that so let gamma be a countable. So let's say I mean it follows if let's say finitely generated group with T, then the cost of this group gamma is 1. And then we can generalize it in the following way. Let's say lambda is a unimodular random graph with T. Then cost of lambda is equal to 1. So here, it's convenient that we have this notion here, then it's probably clear what this means. We take infimum over all graphings which realize this particular URG. So there is no, we don't claim any kind of fixed price property. And yeah.
So property implies confusion.
Yes.
And in my lectures last week for the students, I put a star below to indicate the infimum cost. And I guess it's important for your.
Yeah. So here.
Yes. Below.
Yeah.
Okay. The infimum cost.
Thanks. Okay. So. Okay. So. Let me tell you how we can prove this. So one way to do it would be to use this Hutchcroft-Pete proof, because now we have Glasner-Weiss, which they use, let's say, and try to make sure that it all goes through. And I think I was told that by Miklos Abert in particular that this can be done this way. So this is one way to proving this theorem by taking this proof And now we have Glasner-Weiss because Glasner-Weiss is used here. And you just try to check that everything works as stated. And I was told by people who, that's right, yeah. And I was told by people who know this stuff better than myself that this works. However, we have slightly different proof, which I would say is more streamlined. So let me try to indicate for you how this more streamlined proof works. It is Gabor-Pete approved.
And it's improved, it's even different in the case for groups.
Yeah, yes.
Oh, cool.
Yeah. Yes, so even for groups, it's an interesting proof, I would say. So the proof goes like this. Let G be a graphing, and suppose that we have a partition of the vertex space. So we have pi is a partition, x1, x2, xn, and then we define the Kazhdan constant of this partition as the number of edges which go between parts. So this is the measure of those edges in the graphing, which so x is in some xi, y is some xj, and I is not equal to j. And we say that this partition is Kazhdan optimal if there is the number of edges is minimal possible. So when this Kazhdan constant is as small as possible. So pi is Kazhdan optimal if, so first of all, there is a technicality. I want those measures of those sets to be roughly the same. So I will say that all those measures are in the interval one in this interval, and I want this to be minimal possible. So that's technicality, but the main thing is that the Kazhdan constant of this partition should be the infimum over all h ergodic. So this should be Kazhdan optimal if G ergodic measures are like this, and k pi is infimum over all such. So infimum over k sigma. So H is ergodic and star holds, where star is.
So you're varying the graphing and the partition, or?
Yes, I vary the graphing and the partition. Yeah. And now Glasner-Weiss says that Kazhdan optimal partitions exist. Glasner-Weiss, Kazhdan optimal partitions exist for every n. And the key lemma is that if we have a Kazhdan optimal partition, so if pi is Kazhdan optimal, then there exists a part xi such that xi has almost unique clusters. So let me just tell you what this property is, and I think I'll finish there. So it means that we have this set. I can just look at my graphing, my connected component, and I can look at vertices which are in the set. So my set xi just give me a vertex marking. And now I can look at the connected components of those. And almost unique clusters means that in each connected component, there are just finitely many of them. Okay, and then it is known, it is classical that this key lemma is enough to deduce that the cost is equal to 1. So really, this is where the job is done. But I don't want to sort of botch it. And if somebody wants, then it's a one-line argument. So I'll finish here. Thank you.
Yeah. So can you say a little more about how you're applying Glasner-Weiss here? Because first of all, so why doesn't this prove fixed price? I'm confused.
So I mean, so we have a sequence of partitions on different graphings, which have better Kazhdan constant, and we take a local global limit of those graphings, so that the Kazhdan constant converge also.
That's what this exists. There. I see. There exists.
For every n, there exists the Kazhdan
Yeah,
optimal
but you're
partition.
changing the space and the action. I see. Okay.
I couldn't read very well what you wrote there, so what do we know about these parts? Just, I can't read it.
Here,
I know about this x1 and up to xn, so they are.
so okay, so G should be ergodic. So we have,
ergodic.
yes, the measures should be roughly the same. So this doesn't matter exactly, but they should be roughly the same. But crucially, if you take any other partition anywhere else which gives you the same URG, this should be the minimum. This should be the infimum of all the. So the number of edges between the parts is smaller than in any other partition into an.
So you cannot bound individually, but the boundary, but it's optimal amount. Optimal.
Yes, it's optimal.
Boundaries.
The total optimal is
And parts, essentially.
yeah, and parts with those constraints.
I just wanted to make a small comment that a student of Théories and Alice Giraud, she had also a version of Connes-Weiss for different purposes.
Yeah, I meant to make this comment. I'm sorry. Yes, so there will be some independent work about Connes-Weiss in a slightly different setting, more about full groups, as far as I understand.
Are you able to prove anything about these measured triangulations?
Say it again.
Are you able to prove anything about this measured?
Okay, so now I mean, now we can say that, okay, this thing which we get as a limit, it has T or it doesn't have T. If it has, then well, the gradient is 0. Right? So in a way, for this gradient question, you can ignore the ones with have T.
I have one more. Earlier, you said that there is a deterministic. You have graphs that weren't Cayley graphs. I guess
Yeah.
that have property P.
Yeah,
But they're vertex transitive graphs.
I believe so.
Is
Yeah,
that this equivalent to saying that their automorphism group has P?
that sounds very plausible. But I mean, the way it's done is via Żuk's criterion. So one would have to sort of investigate it in this way.
One more. Okay, if not, then let's think over it again.